All right, let's dive right into this explainer. Today, we're exploring a geometric concept that is honestly pretty mind-bending. We're going to look at how complex space is, whether we're talking about the 3D architecture of ancient sacred sites or the trillion-parameter AI models running today, are driven by the exact same mathematical gravitational pull. For those of you already fascinated by structural analysis, get ready because we are focusing heavily on the ultimate mathematical attractor, the isotropic zero-point state.
To help us conceptualize this massive shift from tangible ancient structures all the way out to continuous AI networks, here is our roadmap. 1. The zero-point attractor. 2. Measuring geometric closure. 3. Structural analysis in antiquity. 4. Pathways of symmetry. 5. The geometric routing hypothesis. And finally, 6. Intelligence as geometry.
Section 1, the zero-point attractor. We really have to start by establishing our fundamental anchor point before the math gets too complex. So the absolutely crucial thing to grasp here is that this 0 point isn't just some static number written on a page. Think of it more like a dynamic, mathematical gravitational center. The isotropic 0 point state occurs when all dimensions in a given space are perfectly equal, right? So in a three-dimensional room, that's a perfect cube. In a probability space, it's a perfectly uniform distribution. And what the math tells us is that structural forms naturally regress toward this state. It's an attractor. It literally pulls diverse, irregular geometries toward reconciliation, stability, and ultimate closure. Section 2, measuring geometric closure. Now that we know exactly what the center is, this perfect state of isotropy, we need a rigorous mathematical tool to measure how far a structure has departed from it. When we try to measure this departure, a standard Euclidean metric is frankly just too crude. Drawing straight lines in complex space just doesn't work. Instead, researchers realized we absolutely have to upgrade to Riemannian geometry, specifically using the Fisher information metric. The Fisher metric treats the 0 point as a privileged center, which means a structure's path to get there is measured as a natural, curved space geodesic path, rather than just a rigid straight line. Using this curved space math gives us our central equation, the mathematical closure score, or sigma. This is a brilliant dimension-independent way to measure things. Reaching a perfect 1 means the structure has fully collapsed into perfect stability. It has actually hit the 0 point attractor. The smaller the score, the more anisotropic or stretched and unresolved the structure is. It's a scale-free way to measure exactly how much pull a structure has surrendered to. Section 3, structural analysis in antiquity. Let's see what happens when we apply these exact equations to physical history. It's one thing to have a neat Riemannian theorem sitting in an academic paper, right? But we have to ask, does reality actually cooperate with this mathematical model? Did ancient builders unknowingly or perhaps knowingly construct spaces that obey this invisible isotropic pull? Well, looking at the closure scores, reality is absolutely cooperating. When we run the dimensions of ancient canonical objects through our closure functional, it doesn't just spit out random noise. Take the most holy of the tabernacle, essentially a perfect cube of 10 by 10 by 10 cubits. It hits the exact mathematical 0 point, a perfect 1.0000. Other canonical objects, like the Great Pyramid's Queen's Chamber and the Ark, form non-random, highly ordered clusters with scores sitting tightly in the 0.99 and 0.95 range. Meanwhile, elongated structures like the whole tabernacle trail way behind at 0.6667. Reality, it turns out, is highly geometrically structured. Section 4, pathways of symmetry. Having seen the incredible clustering in that data, we need to understand the distinct geometric channels these structures take to approach the center. The data reveals a truly fascinating narrative. Structures don't just float randomly toward the 0 point. They funnel through highly specific geometric families. First up, we have exact closure forms. These are the true 0 point spaces that have fully succumbed to the attractor. Second, we have near closure square forms. They sit incredibly close to the origin but maintain a slight directional stretch. And finally, we have the elongated carrier forms, which are deeply unresolved, extended spaces strictly designed for processional transit, essentially carrying a subject toward the closure point. To map all of this mathematically, researchers added a second invariant called tau, which represents the symmetry class. Think of this as the missing key for structural analysis. By adding tau, our model perfectly classifies whether an architectural form was designed for neutral closure, processional transit, or vertical ascent. So we now have a full mathematical mapping of physical ancient spaces and exactly how they obey the 0 point attractor. Section 5, the geometric routing hypothesis.
Okay, let's completely zoom out from the 3D space of antiquity and apply this exact same isotropic pull to multi-agent artificial intelligence. In modern AI, large language models are frankly starting to struggle under their own weight. As neural parameters scale up into the trillions, doing the math for every single connection, what we call dense matrix multiplication, becomes physically unsustainable. The problem of scaling multi-agent AI networks is miraculously solved when we treat routing as a deterministic phase transport problem, guided by the very same geometric principles we just looked at. This is the geometric routing hypothesis. Information flows across a high-dimensional curved space, drawn naturally toward mathematical attractors rather than relying on stochastic guessing. To actually make this work, the AI's internal space has to be rigidly bounded by a complex metric. It relies on a principle called the contraction mapping theorem. In plain terms, this formula guarantees that as network trajectories bounce around, they are algorithmically forced to compress toward a solitary fixed point, rather than decaying into chaotic fractal noise. It forces the data to collapse toward the center, acting as a sort of algorithmic gravity. But computing in a curved, high-dimensional space requires completely new tools. Standard flat space math just fails here. If you try to add straight vectors in a curved space, you end up flying right off the manifold. To fix this, systems like the prime R4 router replace standard math with the Mobius gyrovector addition equation. This elegantly complex formula keeps the AI's data securely bounded, successfully executing continuous neural routing on its curved path right to the 0 point. Now, early models actually tried to collapse the math, which unfortunately ended up destroying precise positional data. But researchers fixed this by operating in a non-collapsed, complex Riemannian manifold, which is essentially a four-dimensional space. By utilizing this continuous, non-Euclidean state space carved out by the natural distribution of prime numbers, the system achieves incredible speed. The AI routes data like water flowing through a valley of minimal curvature, organically drawn towards stable prime triplet anchors. It actually gets more efficient as it coordinates massive autonomous agent swarms. Section 6: Intelligence as Geometry. Finally, let's tie all of these mathematical, architectural, and computational threads together into one ontological reality. Consider the continuous operational cycle of the prime R4 router used in these massive decentralized AI hives. It ingests state data via the 2i bridge, evaluates oracle boundaries, performs conformal phase alignment, quantizes the distance radially on stable Mersenne shelves, and finally projects an output. This sequence reveals something totally staggering. Multi-agent LLM reasoning isn't random black box magic. It's simply physical propagation along geometric valleys toward an attractor. It is the exact same math, the exact same isotropic pull that governed those ancient qubit spaces, just applied across trillions of dimensions. And this brilliantly illustrates our core takeaway. Within this topological framework, what we call intelligence, or reasoning, is strictly equivalent to discovering the shortest, collision-free geodesic path across a curved geometric space. Whether we are talking about the perfect qubits of an ancient altar resting at a mathematical closure score of 1, or the parameters of a decentralized AI hive routing data, true optimization is simply the mathematical collapse toward the isotropic 0 point. Which brings us to a pretty radical conclusion proposed by the research. Quote, "Intelligence is an inherent regime of geometric information dynamics, not an exceptional biological addition." End quote. If cognitive insight is just the phase closure of high-dimensional branches snapping into a stable invariant loop, driven by the inescapable gravity of the 0 point attractor, what other mysteries of the universe are simply waiting to be unlocked by the pure gravity of geometry? Keep exploring, and I'll catch you in the next explainer.